So you can start whenever you want.
So let me continue the lecture with constructing the action of string field theory. And let me actually start simply by constructing the action of free SFT. So that is just a kinetic term for the string fields. And so to streamline the discussion as much as possible, to avoid complications, let me stay in the bosonic world. So, of course, there are also formulations of string field theory for superstrings. There we have to deal with additional complications having to do with the distribution of picture changing operators and amplitudes, etc. So the starting point for us will be the BRST quantization over worksheet sigma model. So WS will be just worksheet. So for that, we need to choose a consistent background on which the string propagates. And the main idea behind constructing the free action for the string field theory will be to identify the condition on a state in the worksheet CFT to be physical, with the equation of motion of the free SFT. That's one guiding principle. And the other guiding principle will be to think of the BRST, global symmetry of the worksheet action, as being lifted to gauge symmetry of the SFT action. Which should be thought, as I was trying to explain, with each physical state, we should associate a string field, and the action for that string field should be thought of as living in the target space, in the space-time in which the string propagates. So the action for SFT should be thought of as action on that target space, and we will see that the BRST symmetry on the worksheet will translate into quote-unquote BRST gauge symmetry of the string field theory action. So just to illustrate with a simple example, in particular to illustrate this first point, we can just consider a free scalar. So in free scalar, we know that the on-shell condition k squared equals to minus m squared is equivalent. So the on-shell condition of this, which we impose on this free scalar particle, is equivalent to the corresponding field equation of motion of the free scalar field theory, which is just the Cohen-Gordon equation, which of course can be derived by varying the free action for a massive scalar. So exactly the same logic we will try to apply in the case of a string theory. So, assuming that we've already been through this process of BRST quantization of the worksheet, what we end up with is the gauge fixed worksheet theory, where the gauge symmetry which we have fixed was the reparameterization symmetry of the worksheet. Theory. And this gauge fixed worksheet theory is just a CFT of the meta sector and a CFT of the corresponding Go system, which we introduced in order to fix this reparameterization symmetry. So when I write this like that strictly speaking applies just to the Go string. If I want to describe also the open string, I have to consider Riemann surfaces with boundaries, and on those boundaries I have to impose some conformally consistent boundary conditions. So in that case, I'll be working with BCFTs. So we can also add this little b in the bracket where b stands for boundary. So the CFT matter can basically be whatever you like. I mean, in the very simple examples, which one usually considers in a first course in string theory, the CFT matter is just a bunch of free bosons, which will describe compact or non-compact flat directions of the target space in which the string is propagating. But really, this can be anything, anything except for the fact that it has to have total center charge equal to 26, which is exactly to balance the center charge of this ghost CFT, which is just the usual BC Go system, which I will review in a moment, and that has a center charge of minus 26. So the total center charge on the worksheet.
Does it have to be unitary?
This thing?
Yeah.
No. Time-like free boson is not unitary. Right. Can be for anything. So then, as I've just promised, let me recall a few basic facts about the BC Go system. So that is a CFT which is actually given by an action. Not all CFTs actually can do that. The action is as follows: B del bar C plus B bar del C bar, where B and C are fermionic fields with scaling dimensions 2 for B and scaling dimension -1 for C. And as I was saying, these are Grassmann out. So then I can study some details about this CFT. Let me write down the mode expansions for these two fields. So these are flowing go-round series, which precisely reflect the scaling dimensions of the two fields. So from that, you can also read of the corresponding action of the modes on the SL2 C invariant vacuum, which in the case of the B modes, you can split the modes into creation and annihilation operators, where the modes annihilate the vacuum for n greater than -2, and in the case of the C modes, they annihilate the vacuum for n greater than +1. Again, reflecting the scaling dimensions of the two fields. So then, in order to be able to compute correlation functions in this CFT, we have to know what the OP of these two fields is. So the OP of B C is just 1 over Z minus W plus radial terms. CP. From which it follows, and that can be translated into the mode language, that the anticommutator, which I will be writing as a graded commutator of the B and C. So I will never use the curly brackets for anticommutator. I will always assume that I know what the Grassmann-ality of the modes is, and I will just write it as a commutator. Thinking of it as analytically. So this is gradient. Now another useful piece of information is the 3-point function in this theory, which is the following. Which again can be translated into the language of modes. So computing the following overlap of the C modes, I can normalize it so that it is equal to plus 1. So in particular, one thing to notice is that in order for any correlator in the BC goes CFT to be non-zero, I need to require that at least at the level it has ghost number 3. So ghost number, that's an additional concept which I want to introduce, is a quantum number in the CFT which is associated to a conserved current, and it assigns value +1 to the C ghost and the value -1 for the B ghost, so that exactly as I was claiming, when I have 3 C ghosts, I have ghost number +3, and the associated conserved current, you can quickly verify this is just minus BC normal ordered. So then, given these facts about the BC ghost CFT, we can write down some representatives of typical states in this combined matter ghost Virtual CFT. So these are the typical string states. So now let me separately go through the case of the open string Hilbert space and a ghost string Hilbert space. So in the case of open strings, I can write down a generic state in the Hilbert space as follows. I can act with some C ghost creation operators, some B ghost creation operators on some generic state in the boundary conformal field theory Hilbert space of matter. So this is a completely generic representative of this Hilbert space, and later we will see that it is very useful to assign a grading degree to these states, which in the case of open string states I will just define to be the total ghost number +1. So this is for later. Now for the ghost strings, so this is open. For ghost, you could say, okay, so let's so while the open string states that are just formed from holomorphic part of the BC ghost CFT and the BCFT matter, which is itself just holomorphic. Then for the ghost string, let's just take 2 copies, holomorphic and anti-holomorphic, and that's that. But there is an additional complication. So first of all, let me just write down a naive representative, which is just doubling the number of degrees of freedom, basically. And now this state phi is generic state in CFT matter, primary or descendant, whatever. And similar to the open string case, we will assign a particular grading to these states. And for the closed string, that will be just the ghost number. With no +1. So now, the additional structure, or the additional constraint which I need to impose on the closed string states is the level matching, which is reflected both at the level of the matter CFT as well as at the level of the ghost CFT. So the constraints are as follows. So I need to require that L0 minus, or L0 minus I define to be, just the difference between L0 and L0 bar of the total worksheet CFT. So L0 is the zero mode of the stress energy tensor in the worksheet CFT of matter and ghost. So it's the sum of the zero modes of the stress energy tensor in the matter and the ghost. And this L0 minus, I need to require that it annihilates the closed string states. Not only that, I need to require an analogous condition also for the B0 minus, where B0 minus is defined analogously as L0 minus, but for the B ghost. So B0 minus is going to be just B0 minus B0 bar. So now, these are representatives of generic states in the worksheet string theory Hilbert space. But then, of course, not all of these should be associated with physical string states. So in BRST quantization, the condition which we need to impose on these states in order for them to be associated with physical string states is formulated in terms of an object which is called BRST charge. Which, again, I will write down separately for the open and closed case. In the open case, this is defined to be just the contour integral of a worksheet current, which is called the BRST current. So JB is a field in the combined theory of the matter and ghost CFT, which can be written as the C ghost times the matter stress energy tensor plus the normal ordered product of B, C, del C. So then, similar as we are assigning some degrees or grades to the states and the Hilbert space, we can also assign definite degree to operators acting on that Hilbert space. So this Q, that is an example of an operator which will act on these states. And in the case of operators, both in the closed and open case, we will say that the degree of an operator is exactly equal to its ghost number. So in the case of Q, you can read off that the ghost number is exact, that it's homogeneous in the ghost number and is equal to +1, right? So here the +1 comes from the C ghost, and here the +1 comes from 2 minus 1, right? So then, in order to be able to do practical computations with this QO, let me also give you the values for form, decomposing it based on its content of B naught and C naught. So it can be written as B C naught L naught times B naught some operator M plus some operator Q hat, where L naught is just the zero mode of the total worksheet stress energy tensor. Now M is a certain combination of C ghosts, which can be explicitly written as follows. And Q is yet another combination of modes and ghosts. Create some space for that. So that's going to be equal to C minus n Ln, where these modes Ln, these are just the modes of the matter stress energy tensor. Plus, minus a half sum over m minus n, c minus n, c minus n, b n plus n. And the sum is taken over all mn such that m and n are not equal to 0, and also m plus n is not equal to 0. So that is an explicit expression for the BRST charge in the open string case. And then you can do some exercise with that if you like computations. For instance, you can prove that the condition that we are imposing, actually the only condition which we're imposing on the matter CFT so far, and that is that it has sensor charge 26, guarantees that this BRST charge is nilpotent. So you can try taking this expression for the BRST charge. You can try to square it, and what you find is that is equal to 0. Another useful property which will see a lot in what is to follow, and which directly follows from this decomposition of the BRST charge, is that when I take an anticommutator of Q with B naught, what I will end up is just L naught. So that is very simple to see. So the only thing which this B naught sees is of course the C naught. That follows from this fundamental commutation relation in the BC goes CFT. The only non-trivial commutator of B naught is that with C naught. So when we anticommute this B naught with Q, the only thing which we detect is this first term.
Is that L naught matter or L naught of the whole?
That's L naught of the whole. That's total L naught. That's the L naught of the whole Hilbert CFT. So now in the ghost case, the generalization is pretty straightforward. Instead of just taking a holomorphic combination of modes for the BRST charge, we define it to be sum of the holomorphic sector plus the anti-holomorphic. And again, we could kind of write down a similar decomposition as we did for the open case. By this time, it is already good to use the fact that we will only ever need to act with this QC of states which satisfy the Sutton matching constraint. So using that, we find that we can actually write this as C naught plus, L naught plus, B naught plus, some M, and some Q hat. The operators with pluses are defined analogously to the operators with minuses, but replacing this minus with a plus. So C naught plus, for instance, would be actually 1/2 of C naught bar plus C naught bar, and B naught plus would be just B naught plus B naught bar without the half. So then again, we would have an analogous property to this equation in the open string case, and that is QC anticommuted with B naught plus would give us L plus. So that's the BRST charge in both the So using this BRST charge, you can finally formulate the condition of a state in the rigid CFT to be associated with a physical state of a string. And following the usual BRST prescription, we are instructed to associate physical states with the BRST cohomology at a specific ghost number, which, in the language of this grading which I was introducing, turns out to be associated with degree +2 for both the open and closed string case. So this is one of the advantages of introducing this degree instead of just working with the ghost number, because you see that if you were working with the ghost number, the cohomology would have to be specified at different ghost numbers for open and closed strings, whereas if we work in terms of this degree, we can just say that it's degree +2 for both. So this is as good as saying that a string state phi is physical if it belongs to the kernel of Q, modded out by the image of Q, which of course is a subset of the full Hilbert space at degree +2, and that in turn is as good as saying that phi is physical if and only if A, it is scaled by Q, and B, we are instructed to identify physical states which are represented by phi, with physical states represented by phi, plus some state which is Q exactly. So these two string states will be giving rise to the same physical state of the string. By lambda, well, we remember that Q had a degree +1, and in total phi has to have degree +2, so lambda is now any string state with degree +1. So now before trying to implement this idea of associating the physical state condition with an equation of motion in string field theory, let me just quickly give you some typical representatives of physical states in string theory. So for the sake of definiteness, let me focus on the open strings. So typically I can write down a state of the following form. So it's C1, V0 acting on a vacuum, where C1 is the +1 mode of the C ghost, and V0 is a field in the matter. Okay, to emphasize that it's in the matter sector, let me put this M in the brackets. It's a field in the matter sector which has scaling dimension +1, and it is a primary. So it's dimension 1 metric primary. So given everything I told you about the BRST charge, you can act with the BRST charge on that state, and you can prove that it kills that guy. And in particular, if the CFT matter can be decomposed as a CFT of a bunch of free bosons, which are associated with some non-compact flat directions in which the string propagates, plus some CFT compact, which describes the rest of the target, which can be compactified, right? Then this V matter can take a particular form, right? We can write it down as some field phi, which belongs to this compact part of the matter CFT. times the plane wave in these non-compact free bosons. So that thing will be a metric primary as long as so that thing will actually will always be a metric primary. Then of course I can also consider some boson oscillators in front of this exponential. Then I would have to satisfy some additional conditions in order for that to be primary. But that is a very simple example of what would have been a metric primary, right? And it will be weight 0 as long as I satisfy the condition that the dimension of this field phi, which lives in the compact part of the Hilbert space, plus k squared, where k is the momentum of this plane wave, is equal to 1. So for states of that form, you can actually show, as I was telling you, that when you act with Q on that guy, you can pretty much immediately see that the action of Q in this case reduces to just acting with C naught L naught, where L naught is, since it is the zero mode of the total worldsheet stress energy tensor, it just measures the scaling dimension, which in the case of that particular state is k squared plus h phi minus 1, where this h phi is for the dimension of that field, and that minus 1 is for the dimension of this C1 C ghost mode. So this h phi minus 1 is what people usually call m squared, as the mass of the associated string states. So that allows you to write the action of Q as just acting with k squared plus m squared. So then you can immediately see that that the requirement that Q kills the vacuum is as good as requiring that the momentum of this plane wave is put on shell. So this is how you make contact between this kind of abstract way of phrasing the on-shell condition with what you usually know, or what you usually encounter in field theory.
Is the statement that there's a basis for this Q cohomology which takes that form always?
Yes. I was just about to describe this. Actually, yes, with some caveats. I think the statement is true for open strings. For closed strings, there are examples of states, of physical states, which do not take this form and for which there is no representative of cohomology of that form. That is the ghost delta. I will talk about the ghost delta later in the course. But in general, what I can say is that the generic statement which we can say is that there always exists a representative of the cohomology, which is scaled by L naught, which is total worldsheet conformal dimension 0. So in the open string case, we can say that it's scaled by L naught. In the closed string case, it will be scaled by L naught plus, right? And
can you remind what is L naught plus again? Can you
so L naught plus is just L naught plus L naught bar. So it's an operator whose eigenvalues will be the scaling dimensions in the closed string. And the way to see this fact is as follows. So from this condition B, you can see that the cohomology is always defined, or the states in the cohomology are always defined after an addition of something BRST exact. And it's something which indeed you'll in a moment try to interpret as kind of a gauge symmetry of the space-time SFT action. Right? So in order to do some practical computations, what we always do is we try and fix this freedom in adding an BRST exact state. And what can be shown is that a consistent way of fixing this freedom, which can be always achieved by a suitable gauge transformation of that type, is to impose that the string states are killed by V naught. In the open string case, or analogously with B0 plus in the closed string case. And that is called the Siegel gauge. So assuming that we are able to fix the Siegel gauge, you can then see that if we act with L0 on a representative of the cohomology which satisfies the Siegel gauge condition, we can expand this L0 as an anticommutator of Q and B0. And then you see that one side of this anticommutator will kill this phi because phi is in the cohomology, it's Q closed, and the other side will kill because it's in Siegel gauge. So this is a way of seeing that that we can always find a representative of the homology which is in the kernel of L0, which has total Virchie dimensions. So then, let me come back to this original idea of implementing the physical state condition as an equation of motion. So the question is the following. Can we find an action, I will call it S3, where these string states will enter as fields, such that A, when we vary this action, this will impose the condition that Q on phi is equal to 0, and B, this action is invariant under the following field transformation, which just shifts the phi by something which is Q exact. So now the answer to this problem is the following. First of all, let me just, so as to speak, parameterize the answer by saying that it can be written in the following form. At the moment, we don't know what this omega is, well, what it is exactly in terms of some quantity on the worksheet, but I can tell you what its algebraic properties should be, so that this candidate for an action satisfies these two conditions. So omega should be a non-degenerate bilinear form on the string Hilbert space, such that it's graded antisymmetric. So when we act with omega on some string states phi1 and phi2, that is the same as acting on phi2, phi1 with some sign, where the sign is just going to be given as -1 to the phi1, phi2. So here I'm using this shorthand. If I write phi1 and phi2 in an exponent of a -1, what I really mean is the degree of phi1 and degree of phi2. Okay, so it's like d of phi1 times d of phi2. So this is the graded antisymmetry. And the other property which I need to assume is that it's so to speak, BRST invariant. So when I act with Q on one of the insertions of this non-degenerate bilinear form, then again up to some signs, this is the same as acting on the other insertion. So now, given these algebraic properties, you can show that that they are enough to show that this action which I wrote down on top of the board has these two properties. So let me just very quickly do that so that we can see that in detail. So for property A, what we want to do, we want to vary the action, right? So when we vary the action, we need to separately vary the first and second insertion into the bilinear form. So then let me focus on manipulating the second term. So in second term, what I can do first, I can use the second property, the BRST invariance, to rewrite it as minus omega p1 phi p phi. So here I'm picking up this minus, right, because I have just this minus here, because when I move this q past this state phi 1, I need to remember that the string fields, which I'm using to construct physical states, they have degree +2. So this degree here is +2, so that -1 to the phi 1 contributes to the plus, so I just get this minus here. And then I can use the graded antisymmetry, that the first property of the symplectic form, to rewrite it as d phi, d phi. So I've just said symplectic form instead of bilinear form. This is what this omega is sometimes called. So I will be using these two names interchangeably. So then you see that we have managed to massage the second term in precisely the same form as the first. So this plus half just becomes +1. So we get omega d phi q phi. And if we impose that the variation is 0, then we can finally use the non-degeneracy of this bilinear form to show that this implies that q phi is 0. So that is this property A. Now for property B.
In this whole discussion, is phi a completely general state in the CFT matter plus CFT ghost?
So yeah, okay, yeah, that's perhaps something which I should have emphasized. So at this point, we are just trying to build an action which reproduces the on-shell condition as an equation of motion, and we know that in on-shell the degree of that state which enters the on-shell condition should be +2. So in order to mimic that, I should have written this clearly. We should require that the degree of phi is +2. And it is something which we call the dynamic of string field. But up to that, it is a completely generic state in the string Hilbert space. Yeah. By the way, while we are there, we can then also read what the degree of omega needs to be, right? Because we know that s should be just a number, right? Action is just a number. So then we can count phi is degree +2. This is also degree +2. Q is degree +1. So in total we have degree +5. So the degree of omega needs to be -5. Okay. So now for this property B.
Sorry.
Yes.
I thought in the open string case at least that there's this +1 in definition of degree, so it's not clear the degree is additive if you multiply things. Like it is the ghost number which is additive, right? The degree has a +1, so.
Yes.
So
It's
if
additive.
the Gauss number is additive, then the degree is not additive, because if you add two things together, you're going to get +2 instead of +1. Maybe I'm misunderstanding.
Well, but then you see that the degree, I mean, was defined differently for the states and for the operators.
I see. Right. Okay. Yeah, got it.
So, so for this property B, we can already use much of the work which we've done for proving property A. So this field transformation Q lambda is in particular a very special case of a variation, right? So what we did here was for a completely generic variation of the action. So now we can substitute this special variation, right? But now for the special variation, which is supposed to represent the gauge transformation, we need to require that we actually obtain a zero for the generic phi, not just for phi which is on shell, right? So let's see how that goes. So now we can substitute for the lambda phi. So then again we can use this BRST invariance property of the bilinear form, namely that if we act Q with one insertion, then on one insertion, then this is as good as acting with the same Q, but on the other insertion up to a sign. So in this case, you can actually see that this is equivalent to lambda overlapped with Q squared phi, and then this is 0 because we are assuming that our string background is critical. That is that the BRST charge squared is 0. Okay. So this is how this definition of omega ensures that we can mimic these two properties with an action. So now, of course, I have to tell you if it is possible to define omega in terms of some worksheet CFD object. Of course, the answer is yes. And again, it will slightly differ between the open string case and the closed string case. So in the case of an open string, omega open acting on two generic states in the worksheet CFT, and we define as follows. So it is a certain correlator of the BCFT on the upper half plane, right? Where we know from the state operator correspondence of the CFT, we can take for any two states in the worksheet CFT phi1 and phi2, we can construct corresponding fields, which we can insert on the boundary of the upper half plane in the case of the open string. And what I need to tell you is what this conformal transformation I open is. This is the so-called BPZ dual, and it takes z, which is a coordinate on the upper half plane, to -1 over z. Okay? So this, I mean, if I tell you this should be, I mean, with this you should compute any result of this bilinear form for any two states, right? Just act with this conformal transformation on one of the insertions, and compute the corresponding two-point function on the other. And you can indeed prove that it has all the required properties which we listed above. In particular, for the BRST invariance, you can think of acting with Q on one of the insertions as inserting a contour integral of the BRST current wrapping one of the two insertions, and then by contour manipulation you can see that this is equivalent as computing the corresponding correlation function where the contour integral wraps the other insertion. Okay, so by contour deformation, you can show that this bilinear form satisfies this BRST invariance property. Now for the ghost ring.
Jakub?
Yes.
Sorry. You said that phi1 and phi2 they live on the boundary of the upper half plane?
Yes. So these are open string states.
Okay.
Yeah. So these are open string states, right? These are the states, which if I impose the BRST condition, they reduce to physical open string states, so they should be thought of as living on the boundary of the Riemann spaces, right? Okay. So in the closed case, there is a slight modification, which you can see that is necessary just by counting the ghosts. And that is, instead of just acting with this conformal transformation on one of the states, you also need an additional insertion of C0 minus. And the reason for that is the following. So remember, the fundamental 3-point function of the BC ghost CFT was that the correlation function of free C ghost was non-vanishing and was equal up to some normalization to +1, right? So in the case of ghost strings, we of course need to have two copies, the homomorphic and anti-homomorphic copying of the BC ghost CFT. So the corresponding non-zero correlation functions should be C minus 1, C minus 1 bar, C naught bar, C plus 1, C plus 1 bar. Right. Where the C naught bar, you can quickly show that it can be written as C naught plus or C naught minus with a minus sign for sure. Right. But then you have to realize one thing, right? We were requiring that that the states in the ghost string Hilbert space are level matched. In particular, that is that they are always scaled by B0 minus, right? So if the states are always scaled by B0 minus, right, they can never ever contain an explicit C0 minus insertion. But that C0 minus insertion is always needed in order for any correlator of that type to be non-zero. So we need to supply an additional C0 minus insertion by hand, right? Otherwise, we would always get a 0. Is that kind of clear? Cool. So that's why the C0 minus insertion is needed. And indeed, you can count the degree or the ghost number. And since this guy contains two ghosts, this guy contains also two ghosts, right? Then we have one ghost from here. And then, for instance, an example of non-zero symplectic form or binary form would be when I insert a Q here. That would provide an additional ghost, right? So that correctly gives you the ghost number in order for that to be non-zero, right? So in principle, I mean, if these phi's are precise to the dynamical string fields, which have degree +2, this particular symplectic form would be always 0, right? But I can define it by canceling this restriction on the degree or the ghost number of the fields, and in that case, I mean, I could cook up states with arbitrary ghost numbers, so that this guy is non-zero. But what I can never ever restrict is the restriction that these states are level matched. I mean, this is fundamental to ghost string theory.
What you explained before is that everything is going to work as long as omega is only going to be anything as long as antisymmetric and bilinear.
Yes.
So is there some uniqueness statement that this is the only choice? Could we have?
Maybe after some similarity transformation is unique. So finally, just to finish at a nutshell point, let me quickly give you some very explicit examples of the kinetic terms which we construct in such a way for very specific backgrounds in state theory. So the background which I will have in mind, is an open string background, and it's going to be the open strings on a D25 brain. So D25 brain is an example of a boundary condition in open string theory, which imposes Neumann conditions on all the directions. I will take it to be in flat space. So there, in constructing the explicit form of the kinetic term of SFT action, we can always use the fact, and this is something which you can prove very quickly, that the BRST charge commutes with the level operator. Or by level, I mean the total level of the worksheet and ghost CFT, right? So in writing down the kinetic terms for string field theory, I can just proceed level by level without any mixing between individual levels. Right? So it's diagonal in level. So starting with level -1, of course, what we all know that we encounter in bosonic string theory is the tachyon, right? So when we try and write down a state at ghost number +1, so at degree +2 for the open string, the only state which we find basically is the tachyon, which, I mean, if I assume that that all these Neumann directions giving rise to this D25 are non-compact, I can write down as a linear combination, as an integral over all possible momenta these open strings can have with some polarization, which will give rise to the space-time tachyon field, and then C1 e to the ik x tachyon. So we can count the level. You can see that the only thing which contributes to the total level is just the C1, which is precisely at level -1, right? So this is a state at level -1, and the only state which you can write down at ghost number 1. Now at ghost number 0, it is at degree +1. You can think very, very hard, and what you will find that there is nothing. There is nothing which you can write down. So if you want to write down something which has ghost number 0, right, degree +1, then either there cannot be any ghost modes, or there has to be some number of B ghosts and C ghosts, right? But as soon as you try and introduce some B ghost, right, I mean, you find that you have to increase level, right? So the first non-trivial B ghost creation operator is B -2, right? So then if you want to compensate it to be at ghost number 0, you have to add a C ghost, right? But in order to be at level -1, you would have to add a C3, but C3 is an annihilation operator. So there is really no way of writing down anything at ghost number 0. And why I'm telling you this, so at ghost number 0, this is precisely the Hilbert space which would have given rise to the gauge parameters of the action. So this is telling you that there is no non-trivial gauge symmetry for the tachyon, which of course makes sense because tachyon is a scalar, right? So then, if you take the state phi at degree +1, +2, ghost number 1, and substitute it into the action phi p5, what you will find is precisely what you would have expected. So what you first do, you of course take these two states with two different integration variables, some k and k prime. You substitute, and what you find out is that by momentum conservation of k and k prime, you will obtain a delta function. So that delta function you can then use to get rid of one of these momenta, right? And then you can Fourier transform into the position space. So then in the position space, you will precisely find the expected action for massive scalar with an imaginary mass, that is with a negative mass squared, which is exactly what you would have expected from a tachyon. Right. So here I have written this in a suggestive form. for you to really appreciate that this minus box minus 1 is the position, should be thought of as the position space representation of this Q. But then, of course, assuming suitable follow-up conditions, you can always integrate this box by parts, and you can rewrite it in the usual form, where you have del t minus t squared. So then finally, let me very quickly discuss a little bit less trivial example, and that is going to level 0 from level minus 1. So at level 0, things get a little bit more interesting. So again, starting at ghost number plus 1, this time you will find that you can actually write down two different states. So first, there's the state which will represent the gauge field. If there is just one brain in the stack, this will be just an abelian gauge field. If you choose multiple brains in the stack, I mean, things will become non-abelian, but let's keep this very simple and let's not introduce Chern pattern factors for the time being. So this is okay. So now you have to ensure that everything is at level 0. So on top of the C plus 1, we are also introducing these oscillators, which are the oscillators associated with the free boson CFT, representing the non-compact directions. And mu is the space-time index of this flat target on which the string is propagating. And again, we have production on which this acts, inserted at 0. Now, on top of the states, you have also an additional possibility. And that is, instead of acting with C1, you can act with C0. So again, we have gotten something which is ghost number plus 1, or ghost number plus 1, and level 0. So now, going to ghost number 0. So that is into the space which should contain all the gauge parameters of the theory. You will find that there is something non-trivial, as we would have expected, because the gauge theory, the theory of the gauge field on a brain, well, it should be a gauge theory, right? So we expect to obtain a non-trivial gauge parameter, which has the following form. So I'm using the normalization so that I obtain some familiar gauge transformation law. And now if you take this string field lambda and substitute it into this prescription for what the gauge transformation of the action should be, right? So you will substitute this lambda to the right-hand side, and at the same time you will vary this phi on the left-hand side. That should tell you what the gauge variation of this A and of this B is. And you will find precisely what you would have expected, namely that the variation of this gauge field, provided that there is only one brain, is just del mu of this space-time gauge parameter with the lambda, right? Exactly as you would have expected in electrodynamics. But what you also find is that the gauge transformation of this B is the box of lambda. So now perhaps you start appreciating what the interpretation of this B is. It is precisely what we call the Nakanishi output field. So that's the gauge transformation. And finally, you can take this phi and substitute it into the action omega phi q phi. And again, after some straightforward computation, what you recover is the following. Which does not look very familiar perhaps, but you can do some additional manipulations which will involve integrating by parts, assuming suitable flow of conditions so that the boundary terms can be neglected, and also completing squares. And in the end, when the dust settles, you can rewrite it in this following form. From which you can read out first that this B field, this Nakanishi-Waltrip field, is really just an algebraic auxiliary field, which only has algebraic couplings in the action, no second derivatives, right? So you can complete squares like that, and you can see that the equation of motion for this B field is precisely this bracket equal to 0. So imposing this equation of motion, integrating out this auxiliary field, you recover the expected action for an abelian gauge field.
Sorry, Jakub. In the definition of the status phi,
yes,
you have chosen the coefficients of the two terms to get exactly this equation, or how?
Yes. So I have chosen. Okay. Of course, I have chosen. I could have chosen the normalization differential, right? So in that case, I would obtain different coefficients in this action. But then that action would have been equivalent to what I've written down by a single scale, right? So yeah, I think this is a good place to stop.
Are there more questions for Jakub?
Just one. The equation of motion of B will imply the Lorentz gauge.
Exactly. Yeah. So exactly. So okay. Perhaps, okay. Yeah.
I mean, this is a consequence of the Siegel gauge choice, or maybe without the gauge choice.
It is connected to the Siegel gauge, and the precise statement is that at the level of this level 0 action, the Siegel gauge becomes equivalent to the Lorentz gauge, right? And you can immediately see that, right? You see that the term which is proportional to the B field exactly contains a C0, right? So if I require the Siegel gauge condition, that is that the field is killed by B0, right? That is as good as requiring that this B should be 0, right? Because the C0 is the only way of how I can make the action of B0 on phi being non-zero, right? So we can see that requiring Siegel gauge is as good as requiring that B equals to 0, which at the level of its equation of motion is precisely the same as requiring that the mu is equal to 0. So this is how the Siegel gauge for the U1 gauge field is equivalent to the Lorentz gauge.
Okay, well, if there are no more questions, let's thank Jakub again for the very nice lecture. And we'll see each other again on Wednesday.